The mission of Chainlink Labs' research team is to invent the next generation of Chainlink technologies. We are a very hands-on, product and impact-driven team, and we're seeking to act as a bridge between academia and industry, combining innovations and deep insights from the academic world with ecosystem understanding and product thinking, and then distilling all that into practical, secure, cutting-edge technology for Chainlink. Now, we're working on a ton of different stuff, and today I only have 30 minutes, so I will give you some highlights. If you're curious about any of the other areas we are working on, please come and find me at the conference. Before I get started, I want to give credit to the amazing team we have. So what I get to present here today is based on their work, as well as the work of our all-star cast of academic advisors. They are the proverbial giants on whose shoulders we get to stand. Those of you who attended Uri's keynote yesterday learned about the vision of consensus computing and how blockchains are incredible technology, but on their own they're isolated, they're disconnected from the rest of the world, and so they cannot reach their full potential. Now, in consensus computing and in the newly announced Chainlink Runtime environment, we seek to unify blockchains and the external world, and we seek to do that by connecting them via decentralized oracle networks, via DONs, with each other, with the external world, with APIs, and so on and so forth, and to have all that orchestrated by the Chainlink Runtime environment. So all of these little DONs become little microservices, decentralized, secure microservices, performing whatever task is needed, and then they all get composed together and connected to the chain and to the real world to help us achieve whatever overarching objective we're trying to achieve. And this is really cool because, for example, in DeFi, in blockchains today already, DeFi is the arguably dominant use case and would not be possible without such connective tissue, connecting blockchains with price data from the real world. But what's next here is that we're going to bring the ability to program these DONs, to plug your logic into these DONs, to you, the developers in this room and in the wider world. And so I want to tell you a little bit about what's cool with our decentralized oracle networks and why you should be excited to be able to program them soon. So let's focus on the DONs for a little bit. The DONs are, like the blockchains that they augment, consensus protocols, Byzantine fault-tolerant consensus protocols. And what that means is that they're reliable and secure and can operate correctly even if some of the participating nodes are faulty. So in this example over here, I have a node that is crashed, and I have a node that is actively malicious, that could be controlled by my worst adversary. But nevertheless, the overall system, the overall DON, still does its job correctly and is not subverted by these faults. And so intuitively speaking, I think it's kind of cool that this is even possible, that you can have a system where parts of it are controlled by your adversary, and nevertheless, everything continues to function correctly. So now you might wonder, isn't this also true for blockchains? They're also Byzantine fault tolerant. What's special about DONs? Unlike blockchains, DONs scale horizontally. And to give you some numbers here, this is a recent number pulled by our data science team. Chainlink today runs 1,999 production DON instances, each running our OCR consensus protocol. And to my awareness, nobody else has achieved a comparable degree of parallelism. So to continue then in this vein of there being many decentralized, secure microservices, each DON being its own kind of microservice, DONs are also highly flexible. Each DON can be parameterized and configured according to the particular task it is trying to do. So in certain cases, we might have different node sets running different DONs, depending on what's appropriate for the task at hand. But more importantly, we can change the logic that is run by these dons. So we have a base layer that consists of OCR, the consensus protocol or framework developed by the research team at Chainlink Labs. And then on top of that, we can slot in, plug in whatever logic, business logic, product logic is needed for what we're trying to achieve. And the overall composition of that you can then think of as an almost purpose-built consensus protocol that is reliable and secure and that can heavily rely on the foundations provided by the OCR consensus framework. So things like peer-to-peer networking, things like cryptography, things like remaining live even under various network faults and partitions, the consensus core, all of that is abstracted away by OCR, and so it's easy for developers to follow a few guidelines and end up with an overall secure, reliable, composed protocol here. What we're now doing with the new Chainlink runtime environment is that we're opening up that ability to developers such as yourselves and to make that publicly accessible. And so we're making available the production-grade and battle-tested foundation that Chainlink's products rely on. But dons are not just highly flexible. They're also, in order to realize the vision of consensus computing and connect things with each other, built for connectivity. So one example of this is data ingress. I need to take all sorts of messy real-world data, and I need to somehow come to consensus about it. And dons have built-in optimized sub-protocols for this. So in this example over here, we have a number of data sources, and what we can do is we can have the different nodes in the don observe those sources, and then we can aggregate the per-node individual observations into an objective consensus aggregate. And this, for example, is used in products like data streams, where we have different prices and different data sources might not always return a consistent value for the same asset. But it is also useful in other applications, like CCIP. So in CCIP, the different nodes might not entirely agree on what happened on the source chain. Maybe there was a network partition or something else went wrong. And so again, this aggregation step allows us to come to a consistent consensus about what actually happened, about what messages should go from a source chain to a destination chain. It also helps with Byzantine fault tolerance, because as we already mentioned, we need to take into account the fact that some of the nodes in a don might be compromised. And this step allows us to, despite them potentially contributing bad observations into the mix, still come up with a secure consensus value in the end. So now I told you about data ingress, taking data from the real world and putting it into the don. Next, let's talk about data egress, how we can take data that the don agreed on and then send that onward to other systems, such as blockchains or also Web 2 APIs or whatever else needs the secure data that the don created. So in our dons, in the OCR consensus framework, we have purpose-built report attestation and transmission subprotocols that optimize this step of the process. Let me make that more concrete. The report attestation protocol performs a form of signature compression or optimization that allows us to, for instance, cut the number of cryptographic signatures that need to be validated by whatever target system receives the reports from the don in roughly half. And this is powerful because if you consider, for instance, the target system to be a blockchain like Ethereum, where during times of congestion, the transaction fees for signature verification might rise to tens or even hundreds of dollars, then being able to cut that in half greatly improves the economic viability of whatever we're building on top of our dons, on top of the off-chain reporting protocol here. Second of all, there is a purpose-built transmission protocol that allows us to reliably get these attested reports the don creates to whatever target system we're trying to get them to, while again optimizing cost, minimizing redundant transmissions, and still being able to get whatever reports we need to get to the target system get them there in a timely manner. And then finally, I told you about data going into the Dawn, data going out of the Dawn. In the Chainlink runtime environment and in this microservices analogy, Dawns are also built to talk to one another, to be interconnected. And so we can have different Dawns perform different tasks, and they can all be composed together seamlessly by the Chainlink runtime environment so that a developer leveraging the Chainlink runtime environment still ends up with one nicely programmable system, and all these different components that they need, all the different capabilities can all be brought together for them and exchange the data needed to achieve the overall task. So up until now, I've told you about how Dawns are a bit like microservices, how they're very flexible, and how they're very connected. They're also very performant. And this number here I'm particularly proud of. So in our production data streams, Dawn, running right now, the price latency from a price being ingested from data sources all the way to an attested report having been created is 376 milliseconds. And this is a globally distributed system with nodes in Europe, nodes in North America, nodes in Australia, and nodes in Asia. And despite the fact that all of these nodes are carrying out an involved protocol and are all around the world, I can do it this quickly. And just to put that into context, how fast that is, if I take this coin and I drop it, it takes the coin more time to hit the ground than it takes our Dawn here to come to secure consensus about these price reports, despite the fact that this system is distributed around the globe. And what that then means is that our users, such as GMX, can offer their end users a really smooth UX that can compete with Web 2 trading products. But that is far more secure, decentralized, and trust minimized. Because the latency that the user gets to experience can be minimized to the point where it's no longer noticeable for them. So I've told you about the things that we've already done, that are already live in production, and that make our Dawns industry leading. But we're continuing to improve on them. We're continuing to make them better. And so I want to tell you about some of the innovations we have in the pipeline. First of all, performance-based leader selection. In these BFT consensus protocols, in general, you pretty much always have some kind of leader node that is selected to drive progress in the protocol. And depending on the performance of the leader that you select, the performance of the entire Dawn can vary. And so what we're doing here is we're working on ways to cleverly select particular nodes in our Dawn that are doing a more effective job at driving progress, all while remaining robust and secure and maintaining our Byzantine fault tolerance guarantees. And this is quite a tricky problem, but I think that we'll be able to ship a solution for this sometime in the coming year, further decreasing latency and further increasing throughput of our Dawns. Second of all, we're working on an optimistic single-round commit path where we can reduce the number of network trips that need to happen inside the consensus protocol by roughly half, and thereby, again, in the optimistic case, decrease latency, increase throughput, and all of that, again, while maintaining our BFT guarantees. And then third of all, we're working on improved state synchronization and data dissemination primitives inside our OCR consensus protocol. And what that will enable is for bandwidth-intense applications where we need to push through a lot of data, it will improve throughput by orders of magnitude. All of these enhancements we expect to ship sometime in the next year. And because they all affect our common consensus core, they should be available then to everything built on top of it, including for you developers building on top of the Chainlink runtime environment. So up until now, I've told you about the consensus part of consensus computing. But to build a winning platform, we also need to add entirely novel capabilities, entirely novel features to our systems here. And one really important one is privacy. Dawns, blockchains in general rely on having many nodes participate in the system. And that's really good for safety, that's really good for integrity, it's great for reliability, but it's not good for privacy or confidentiality. And intuitively speaking, that is because all the nodes in the system need to process the information flowing through the system. And so every node, of course, can then peek at that information or potentially even leak it. And so the more nodes I add to the system, the greater my trust surface in terms of whom I need to trust for confidentiality becomes. So what we've been working on at Chainlink Labs Research is a new technology called Deco. And Deco leverages advanced cryptography and zero-knowledge proofs to enable us to, in a privacy-preserving manner, have a DON verify information. I'll go into the details in a second. Verify information coming from a private Web2 API. For example, my bank's API that records my bank account balance and account history without the nodes being able to inspect the data itself. And I think that is really powerful if we want to also onboard traditional finance into the Web3 ecosystem and bring those innovations to the wider world. Because without privacy, I think we just have a non-starter. I would not want my private details to be publicly available on blockchains or distributed systems. And indeed, if we look at the data that's out there that exists in these APIs out in the world, the majority of it is in private, is in gated APIs that require a login or a credential to access. And so if we can make that data available to the world, then we can greatly enhance the utility of our systems. And this is something that we hope to bring to you also as a future capability of the Chainlink runtime environment, as a future feature of the Chainlink platform. So let me tell you in more detail what Deco is and how it works. It's a three-party protocol between a prover, a verifier, and an API. And it achieves three properties. First of all, it achieves provenance. So the API here is running TLS, which is the standard transport security protocol used across the internet. And with provenance, the prover can convince the verifier that indeed whatever data is being talked about originated from that API. Second of all, privacy. The prover can transform whatever data it fetched from the API in a privacy-preserving manner so that the verifier, as well as the smart contract here that receives the final attestation coming out of Deco, only learn the minimum amount of information that is necessary for whatever business case we're trying to achieve. And then third of all, and most excitingly, compatibility. So we can plug Deco into any existing TLS API out there. The vast majority of APIs is already compatible with Deco without them having to change anything, without them even having to be aware that Deco is being used. And this is really powerful because if we consider things like adopting IPv6 or new protocols, it takes forever to get the world to adopt them. But here we don't need the wider world to adopt anything new. All the APIs out there can continue using TLS like they already do, and Deco will just work for them. So let me make this a bit more concrete by walking you through an example. In this example, we have a financial institution that wants to prove to a compliant smart contract on-chain that a user on whose behalf it is transacting is not sanctioned and has had their identity verified based on a government identity document. Now, with Deco, the financial institution can pass its credentials to its proprietary identity API, Acme Identity in this example, to the Deco prover. The Deco prover can then fetch information about the identity from the API. So the prover, which runs inside the infrastructure of the financial institution, does learn the information. The financial institution had access to it all along. But now we can run the zero-knowledge part of Deco between the prover and the verifier, and we can transform the information from the API so that we only reveal the minimum amount necessary for what we're trying to do here. And so we are privacy preserving. And so in this particular example, what we need to do is we need to show, one, the user identity was verified, and two, the user is not sanctioned according to the OFAC sanctions list. The Deco verifiers will be cryptographically convinced of this by the prover. And then finally, we can have an attestation that states this. So states ID has been verified, user is not sanctioned, and the source for this information is this trusted identity API. And we can relay that to our compliant smart contract on chain. Now, we've been talking about Deco for a while here at Chainlink. I think the past SmartCon and the one before that, we already talked about Deco. But what's new at this SmartCon is that we're introducing the Deco Sandbox and making it publicly available. The Deco Sandbox takes these different Deco components that I just showed, and it runs the prover and the verifier inside Sandbox hosted infrastructure, and enables a developer to easily experiment with Deco by accessing the Deco Sandbox from the comfort of their web browser. So there's no need to set up any infrastructure. There's no need to do any deployments. You just go to deco.chain.link/sandbox, and you can start experimenting right away. And so now I want to give you a brief demo of what's possible with the Deco Sandbox. And everything I'm about to show you, you could go on the publicly available Deco Sandbox right now and try it out as well. So in this example, we're going to do a similar sanctions check as I already showed in the previous example, but we're going to make things slightly more advanced. We're actually going to have Deco talk to 2 different APIs. And the reason for that is, first of all, I wanted to show that Deco can talk to multiple APIs and prove a single zero-knowledge statement about information we got from multiple APIs. But second of all, I also couldn't find a single API that actually gives me the sanctions information I wanted and that has the identity verification. But no problem. I can just combine 2 real-world APIs and get what I want. So both of the APIs we're going to talk to here with persona.com as well as offacapi.com are real APIs running TLS. And for the purposes of this demo, we just plug into them. We didn't even have to talk to the people who made these APIs. They're just out there, publicly available, and documented. And so we made an account and set up the demo. And I think that's pretty cool because it shows the permissionless innovation that Deco enables on top of existing private API data. So let's look at the example here. This is the Deco Sandbox. This is the page you're greeted with when you log in. And at the bottom here, we have a number of pre-configured examples that make it easy for developers to get started. But today, for the demo, I want to show you how we can actually create a configuration from scratch. So we'll ignore the pre-configured examples, and we will just go on create use case here. We assign a name to our use case. And now we are greeted with an empty configuration. First of all, we need to tell Deco now how we can connect to OFAC API and with persona.com. So we need to configure those APIs in the system here. And so we will go to the HTTPS requests pane and add the details. So here we add the URL for the with persona API. And if you note there, at the end, we have this variable. We have this $, square bracket, inquiry ID. This is a template variable, which allows us to inject secrets into the Deco proof in a way where the prover, as always, can see them, but the verifier then cannot. And we will later fill in a value for this template variable. We also need to add some request headers, as is common when you talk to APIs. So first of all, we need an authorization header, because this is a permissioned API. You need to have an account with it to be able to use it. In the previous example, the financial institution would have been the account holder with the API here. And then we also specify in what return format we want the data from the API to be returned. So now let's go into the template variables. Let me configure values for these variables for the purposes of experimentation. In a production deployment, you could also then fill values into these variables at runtime and kind of for each Deco run, interpolate a different variable value. But for the purpose of experimentation here, I just set them in the UI and I'm done with it. So we set up the appropriate variables. I want to highlight here in particular the authorization header, which is the API credential and which will remain private. So the prover knows it, the API of course knows it, but we do not leak it to the verifier and we do not leak it to the smart contract. And then we are done configuring the Persona API, so now we can try to have the Sandbox access it and see whether everything works. So let's have the Deco Sandbox fetch data from the API, and indeed, when we click fetch here, we see that we got our API response back. We don't need to go into all of the details here, but the point is just we got a successful result from the API. Now we add the second request here, the request to the OFAC API, which gives us the sanctions information. And so again, we go through the same flow. I'll go a little bit faster this time since we already saw what that looks like the first time around. So let's add the URL of the OFAC API. Let's add the request headers, including the API key. Let's also add a request body that specifies which particular sanctions list we care about. It turns out the OFAC sanctions list exists for all sorts of things that are not just people. So for example, I think there's a list of sanctioned maritime vessels, which is clearly not what we care about here. And then we again set the template variables, just like in the previous example. Here we also now specify the name of the person who we're checking. So our Alexander J sample is the one about whom we're making a Deco proof. Now we can again see whether we configured everything correctly, and we can fetch data from the OFAC API. And again, we did everything correctly. The demo was well set up. And here is our response from the OFAC API. So far we've configured the two APIs into Deco, but we're not yet proving anything interesting. We're just allowing Deco to access these APIs. And so now we will configure the actual statement that's being proven. And the way we do that is we set up what's called assertions, which you can think of as Boolean privacy-preserving functions. So functions that can process whatever request and response data was exchanged with the API, but crucially that do not leak that data, but instead only ultimately give out a single Boolean true or false. Everything succeeded or the check did fail. So here we're now adding assertions on the response from the APIs. On the left-hand side here, we have helpfully displayed the thing we fetched from the API just so the developer knows the schema of what the API returns and can easily play with it. And then on the right-hand side, we set our first predicate here, where we just check that the identity verification that Persona carried out against the government ID of our Alexander J sample succeeded. So let's save that assertion. And let's add a few more. Again, I'll go a little faster for the sake of time. So here we added a bunch of additional assertions that basically say government identity verification succeeded according to the Persona API. And this is maybe interesting to note, we store the name of the person in a slot inside the zero-knowledge proof. And the reason we do that will become apparent when we look at the other API, the OFAC API. It's because we need to link together the two API responses to make sure that they're about the same person, and that indeed the person whose ID was verified is the same person who is not sanctioned. So now we will configure the OFAC API, and I'll quickly show how that's done as well. Again, it's very analogous. First of all, we check what's the number of matches against the sanctions list. Is the person sanctioned? We want there to be less than 1, which is to say 0 matches on the sanctions list. And then second of all, as I already mentioned, we need to link together the two API responses and make sure that they talk about the same person. So that's what the bottom assertion is about here. Cool. So now we're almost done configuring things. There's one more small twist we will do. In principle, all the data that is processed in Deco always remains private, and we do not expose anything that is not explicitly given to the verifier or in the statement or claim that is being signed by Deco. However, here, for the purposes of Sybil resistance, and so that I don't just give a single Boolean always that says, yeah, there is some person who is not sanctioned, I also want to include the pseudonymous Persona account ID in what I reveal in the signed statement from Deco. And so what I do here is I explicitly tell Deco, this one particular field from the Persona API response I actually want to expose publicly. So I add the account ID here in my list of public fields. And now truly I'm done setting everything up, and I can go into the run section and actually run this involved protocol. So when I click run configuration, hopefully I did everything right, and things will run successfully. So we run the configuration here, and ta-da, success, everything worked. Let me quickly show you what we see here. First of all, the result is success. So the proof worked, and we know that Alexander J. Sample is indeed not on the OFAC sanctions list and has had their identity verified with Persona. Second of all, we see that the proof took 47 seconds, which might look like a long time, but if you consider that this is a real-world interactive zero-knowledge proof running against responses from 2 real APIs, this is actually extremely fast. And we are using specialized interactive zero-knowledge protocols to make things this fast. So this is a really good value. And then here you see a summary of the statement we proved. We already walked through that previously when I showed the assertions. And also here at the bottom, if we scroll down a little bit, we see what data we're revealing to the public beyond the Boolean value of yes, things succeeded. And that's just here the account ID, which we chose to expose. So to recap, we just, in the playground, saw this entire example working. You could go to the playground right now and also give it a try, and I encourage you to do so. And what's important to highlight here is that, again, this was all done in a privacy-preserving manner. So the only thing that is in the final attestation and the statement that is signed by the Deco verifiers here is what we wanted to reveal, namely the account ID, the verification status, and the fact that the person isn't sanctioned. All the other information remained private from the verifiers and the contract, and only the financial institution, which had access to it all along, and the API know about it. So thank you very much. Please go to deco.chain.link/sandbox and take our sandbox for a spin. And I'm super excited to find out what you will build with it, because it's such a general and powerful technology that I think it's hard to predict what cool use cases people will come up with.